I'm oral historian Mike Chappell. Today, June 4th, 2011, I'm interviewing Dr. John Thunder for the Endocrine Society at its annual meeting being held this year at the Boston Convention and Exhibition Center. Dr. Thunder, would you please tell me a little bit about your family backgrounds?
Sure. My grandparents, if you'd like to go back as far as that, I remember all of them. One, my paternal grandfather, not very well. They were all in Adelaide. They were Adelaide families. My father's family were, I think, originally dirt poor. The name Thunder's Danish, but the matriarch of the family was Florence O'Brien. That's not Danish, that's Irish. And he had a little shop down in Port Adelaide, and I suspect ran a off-license betting shop or something, but they really did very well and amassed relatively a lot of money, so that all four children of my father and his siblings went to the university in Adelaide, and when they turned 16 were given a car to drive to the university and so on. So this was really fairly special in the late 20s, late 1930s. So there were two doctors, a pharmacist and a dentist among my father and his three siblings. On the other side, my maternal grandfather was the man who built the piers from which the Australian and New Zealand and British troops were evacuated from Gallipoli. They were Watson's piers. I'm John Watson Thunder. And he was an engineer, to be in the army and be building piers, but wound up, in a sense, running the railways in South Australia. And he lived to be 100, which is quite... And I inherited his dinner suit, his tuxedo when he died. So he was a man of, rather large proportions. And so at the end of the Second World War, my father had spent the early 40s in Melbourne as a pathologist. We moved to Melbourne from Adelaide, and that's where I grew up, where I went to school, university, and so on. And I was the eldest of a large family of 7 offspring. Father was a hospital pathologist. Mother was a botanist. She had done a master's in botany in the 30s in Adelaide, and I found out after my father died that she'd actually been offered a place to do a doctorate in Oxford. I'm glad she didn't go, because I think the war would have intervened and I might not be here had she gone to Oxford, but whatever. But she was essentially a homemaker with 7 kids. An intelligent woman. She's still alive. She's 97. So that long-lived strain in the family is something I'm counting on. Put it like that. And we grew up in suburban Melbourne. Went to the local Jesuit school, which was a terrific education. Looking back on it, I did Latin and Greek, the very classical things, maths, English literature, and so on. Then physics and chemistry also. And then went into medicine. There was only one university. There was only one university in Victoria at that time, which was the University of Melbourne, which had been started 100 years before. So, they were still waiting for Monash, which was set up around the time I went off to the university, but didn't have a medical course when I started. So I started medicine and was very active in student politics. I thought first-year medicine was extremely boring. And second-year medicine was worse. It was anatomy to the max. It was terrible. So I was on the Student Representative Council, and I was in drama productions, and I was in residential college, and I did everything except medicine. I got honours in first year and passed in second year, but after 1 week of third-year medicine, it was a 6-year course, straight out of school back then, I went and changed and did an honours arts degree in history and politics and philosophy, and then told my parents, who were horrified, of course.
You told them after the fact?
I told them after the fact. But I had a scholarship and I changed it from medicine to arts medicine. So, my fees were paid. That was okay. I wasn't totally... But I was hoiked out of the residential college and taken home and told, knuckle down. So in my fourth year at university, I met my future, now late, first wife. And I thought, oh, God, you can't possibly, think about getting married. That was back in the days when, in your early 20s, you thought about getting married, not like today. On, an arts degree, what am I going to do? Be a librarian or something? I'm not cut out for that. So I went back to medicine, completed the arts degree part-time, and graduated in 1965, which seems like yesterday, but in fact was quite a long time back. Did residence, and then wanted to do research. And I said to one of my mentors when I was a hospital resident, I noticed that all the young women who are my friends, the nurses, they all get nosebleeds at the same time. And I'd learnt during my course that women in institutions, nuns and so on, they tend to cycle at the same time, so they get their period at the same time. And I said, is there some estrogen or progesterone sensitive mucosa in the nose so that these women who brush their nose or would all get nosebleeds at the same time? He said, I don't know, but if you're going to do research, do it properly. Don't do some half-assed project like that while you're going on doing clinical stuff. I'll arrange for you to meet the people at the Howard Florey Institute. So he did, God bless him. And they took me to lunch, which went till 6 o'clock. It was Pansy Wright, who was the professor of physiology, Derek Denton, the director of the Florey, and John Coghlan, who was I think the sort of much of the scientific drive in the biochemical sense at the Howard Florey Institute. Now imagine that now, you've got a PhD student, the professor, the institute director, and in a sense the head scientist, takes this person to lunch. It goes till 6 o'clock. God knows how many bottles of wine were drunk. And at the end, he signed up. I was the second PhD student at the Florey. I was PhD student number 467 at Melbourne University. No university in Australia had granted a doctorate till after the war. Compared with the floods of kids now who are enrolling in PhDs, doing good PhDs, doing good work, etc. I mean, you were a rare bird back then. And by then I was married, and by then I had one, then two children, and my late wife, Kathleen, was working as a student counsellor in school. She was a psychologist, and doing a part-time master's, and so we were busy. And at the end of my PhD, which was in hormones and high blood pressure, I've been very constant, perhaps too constant, too focused. I got a National Heart Foundation of Australia fellowship and went off to San Francisco.
Let me interrupt you for a second. What got you into hormones and hypertension? And
that was, they said, we've got these sheep, we want to know if we take their adrenal glands out or if we do other stuff with regard to the adrenal glands, and we have models of hypertension by constricting the renal artery, will that affect it? Are they able to be hypertensive, with this hormone or with that hormone? That was chosen for me. Nothing to do with nosebleeds or anything like that. So I sort of just fell into that area. And then at the end of 1969, I applied for and got National Heart Foundation of Australia 4-year travelling fellowship, 2 years away and then 2 years back to set yourself up. And the choice of San Francisco, where I worked in Professor Edelman's lab, Dr. Izzy Edelman, a wonderful man, was made for me by John Coghlan, who met Izzy at a meeting in Japan, and Coghlan says, I've got this young fella, we want to send him somewhere, and how does aldosterone work on its target tissues? And we're very interested in what controls aldosterone secretion. So can he come and work with you? Oh, Izzy said, fine, if he gets some money. I got some money from this fellowship. and went to San Francisco. And that was terrific. It was really terrific. I was told, oh, you've got to be careful of these Americans. They will, you know, they work all this time and it's publish or perish and it's desperate and dangerous to go out after dark and so on. And I had 2 kids, and by the time we left I had 3 kids, so I didn't do much going out after dark, but you know, I'd get to work at 8:30 or 9 in the morning and I'd leave at 5:30 to come home with the kids or to help with the kids. And we'd go, you know, travelling on the weekend and do stuff. And everybody was very welcoming. The Cardiovascular Research Institute, because Iz was the associate director of that, was really terrific. It had an equal number of postdocs, which I was one of, fellows, from America and what were termed aliens, which is a bit, you know, space wars, but still. And, you know, that was a policy, half and half. So I met people from all over the world in the Cardiovascular Research Institute and have remained good friends with some of them and with some of my American colleagues. I worked very closely with David Feldman, who's now down at Stanford, a distinguished endocrinologist who went off into vitamin D, you know, which is now having an extraordinary renaissance. Whereas I've stuck with hormones and high blood pressure and hearts and stuff like that. But Kathleen, my wife, was marooned with these 3 kids up in the fog, and she said, oh, I'd love to go to Europe, can't you? So I went off to a meeting in Munich, met people there. They said, come and work in Paris. We do angiotensin receptors, you do aldosterone receptors. Let's see if we can do something useful. So,
let me take you back a little bit still to the CVRI when you were there.
Yeah, sure.
What was, could you say a little bit more about Isidore Edelman and his scientific stature?
Sure. He was a wonderful thinker. He'd trained as a nephrologist, as a kidney doctor. He'd had a stint in the army, trying to find out ways of rehydrating people who were dehydrated and stuff like that. So he was interested in fluid and electrolyte balance. And so aldosterone's what determines how much sodium we retain in the kidney, and with the sodium comes water. So that took him into that. But he'd done biochemistry before he did medicine as his undergraduate career. And he was a very rigorous thinker, and I profited enormously from the training in thinking, yes, but in biochemistry, really. I mean, I'd done undergraduate medical biochemistry, but never a proper biochemistry course like 4 years he'd done. You know, before he went off to medical school in the University of Indiana, because back then, being Jewish, he was, you know, there were effectively quotas in New York where he grew up. So he's a graduate of the University of Indiana, medical graduate from there. I remember celebrating with him his 40th birthday. He used to make sure we always did, if we wanted to do a particular experiment, we did it first on the whiteboard. You know, what's this, what's that, what do you think the outcomes are going to be? Very good training for you know, a scientist in training. I got 11 papers out of 2 years there. That was a terrific, you know, outcome. I'd had a lot of experience writing, put it like that, you know, with that very varied degree in student politics and arts and philosophy and stuff like that.
What research did you do with him?
We did some of the very earliest stuff on the receptors, the keyholes into which aldosterone goes to turn on what it does in the kidney, but also in other tissues too, like the salivary gland, because aldosterone affects the amount of salt and water that comes out, not so much in us, but in ruminants. Back at the Florey, back in Australia, I'd worked quite a lot with the preparation in the sheep of externalizing the parotid duct. So drip, 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 and you know, a good dripper, a sheep that was really chewing its cud all the time and dripping out of one side and, wetting the cud with the other one, could lose, 2, 3, 4 litres of saline a day of, quite sodium-rich fluid and become quite sodium deficient very quickly without, diuretics or messing about. So we'd used that a lot as an experimental model back there. So we were interested in a bunch of stuff, but it was about aldosterone, mineralocorticoid receptors, and a bit about glucocorticoid receptors. And they were very early days. Back then.
And you were able to publish a lot of that?
Got 11 papers out of that.
And how did that experience affect your career?
Well, I think it sort of set it in stone. I mean, there's a limerick. There once was a man who said, "Damn, it is borne upon me that I am an engine that moves in predestinate grooves. I'm not even a bus, I'm a tram." And I think I was a tram in a sense from then on. Now, I've had excursions into other areas of science and of sort of scientific side issues, from neuroendocrinology to medical ethics to some cancer stuff and so on and so on. But it's always been, the tram tracks have always been there. Mm-hmm. It's always been cardiovascular endocrinology.
So after completing 2 fellowships, why did you choose Prince Henry's Hospital to return to?
Well, it's complicated. I'd done a year in Paris, at the request of my wife, and that was terrific. All 3 of my children, one was tiny then. We went back for a year, a few years later, as a visiting professor. All my children speak fluent French. And one of them, the eldest, I'm told by my French friends, without any accent, you can be mistaken as French. Because they went to the local school, and then 4 years later went back to the local school. I went back to Prince Henry's rather than the Florey, because at that stage the Florey had very tight, rigid notions about who did what. And if I went back to the Florey, my role was to be the scribe. I wasn't going to do any experiments, I wasn't going to plan the experiments. I was just going to get everybody else's results and write them up. They had a way of publishing which was alphabetical. And that's, insupportable, frankly. If you do the experiments, if you plan the experiments, if you do the work as a young postdoc or, aspiring, you want to be first author. A little later on, you want to be last author and have your students or fellows, taking the front position. That's absolutely normal. There are big papers with 100 authors where, the authorship doesn't particularly matter because it's all been put in from everywhere. But basically, they're the rules, and the Florey was still batting under some archaic English system of alphabetical authorship. So I said, no, I didn't want to do that. I wanted to plan my own experiments and so on and so on. Oh, no, that's not possible. Good-o. So I went to Prince Henry's.
And what were your responsibilities at Prince Henry?
I, set up a lab, wrote grants, got students, got postdocs, just did the normal sorts of growth things that you do. I also set up because I'd had these, the experience of doing mineralocorticoid and glucocorticoid receptors, studies on them in San Francisco and in Paris for a year. I set up a service to measure estrogen and progesterone receptors in breast cancer specimens as a guide to subsequent treatment by the oncologists. And that's a compensable thing. People can get it off. We have a national health system in Australia, so it doesn't come out of their pocket. And thus I was able to generate some money which went into a very good, what was called a special purposes fund. The wonderful thing about that was that it paid for books, journals, but also, really, if you were prepared to go coach, an immense amount of travel. Some of the senior specialists, contributors to that fund, would only travel first class with their wives. So they would exhaust their travel fund in one splurge a year, going to London. I used to get about 5 trips a year out of that fund, which for a young investigator was fantastic in terms of being able to network, largely here, but also in Europe. Less actually in the UK than in continental Europe, but mainly here in the States. That was really an immensely important part. I mean, Henry Berger, my boss at Prince Henry's, was also part of that. His consulting fees as an endocrinologist went into that fund. That was very important. As in the mid-70s and the 80s when I was at Prince Henry's, that the ability to do that, of everybody, the people who made a lot of money, the clinical chemists and the imagers and so on, put it in, and the people who didn't make I actually did all right but other people who see private patients once a week would put in, and they'd get more than they'd put in, and the big people, chemists, pathologists and so on, they'd take out less than they put in, but those days are gone. It's now, everybody for himself. But it was a wonderful way to be able to become international. Yeah.
What were your overarching research goals when you got there?
I think it was always to work out, there were enigmas, questions that came up from stuff we did in San Francisco. How does this thing work? How does aldosterone work? It circulates at 1,000th the concentration of another hormone, cortisol, which fits equally well into the receptor, into the keyhole. So, on probability grounds, aldosterone is never going to, one time in 1,000 going to get in. So that was, really a very important driver of what we were doing. I mean, there was a lot of what I'd call bread and butter stuff. You do things, you measure aldosterone and receptors in any tissue you can think of, in any animal you can think of. That gives you your sort of turn of the wheel papers. But that was a driver, and that came through over the next, 10, 15 years. The answers, they're not all in yet, but the answers started to come through. And, bits that are now in the textbook started to, come out of the work that students, fellows, postdocs did in the lab, and that was terrific. So I think it would be, it sounds a bit grandiose, but it would be fair to say that what drove it was wonder. Just wonder at how all this worked, how all this fitted together. I think if you to do science, this sort of science, biological science, without a sense of wonder, it must be like how, what Cat's vision's like, everything's grey. Whereas if you've got a sense of wonder, if you can look at a result coming out of a, beta count or a gamma counter and say, nobody else in the world's ever actually known this before. Oh, that's a big charge, a really big charge. That's lovely. Yeah.
Would you talk about your discovery of the mineralocorticoid receptors in non-epithelial tissues, what the significance of that was?
Okay. It's been a long and unfolding and still incomplete story. Classically it was thought, there was a hormone, aldosterone, and what it did was to maintain sodium balance, and with it potassium went the other way and water came with the sodium. And so it was pretty heretical to say, well, hey, but they're in the heart and they're in the brain and all sorts of places. And then the question came up, well, what's aldosterone doing there? Because it goes up in response to sodium deficiency, goes down in response to sodium repletion, but, that's not something that the hippocampus of the brain, which is concerned with affect, cognition and all sorts of stuff. It's not linked into that in any sort of loop. And I must say that in many tissues it's still not clear. In the heart, for example, we've got very good evidence of what happens to those receptors, what's driving them, pathophysiologically, in heart failure and high blood pressure and so on like that. That's not universally agreed on mechanisms, but, it's there and clearly it's happening. And whether it's aldosterone or in the context of tissue damage, cortisol, which I think there's a lot of evidence for. But the brain is still terra nullius. It's terra incognita. It really doesn't belong to anybody in this domain. I mean, beaut things are happening in neuroscience. That's not to say that's not the case, but really it's and in a host of other tissues, we've really got very little idea what they're doing. In macrophages, white blood cells. Now there's all sorts of stuff happening about, if you knock them out in macrophages, blood pressure doesn't go up in response to salt and exogenous aldosterone. Hey, what's all this about? So, for every answer there are two more questions. So that wonder is really comes good. I just a very itchy nose.
So, let's see. When you made that discovery and found them in the heart and the brain, okay, what did that do to the field?
Well, the important thing was, I think, to show, and we did, that what had been called corticosterone preferring receptors in the brain, distinct from the regular glucocorticoid receptors, were actually identical with the mineralocorticoid receptors in the kidney. And so that opened up a field of asking questions, what the hell are these things doing in the brain? And a lot of people have worked on that, and I think it's fair to say that there's still more heat than light in answering those questions. But then it was, a parallel thing, and probably even more of a driver, was still, how does aldosterone ever work in the kidney, where we know it works? I mean, the proof of the pudding's in the eating, it works. And then that came in the late 80s with the demonstration in my lab and in Chris Edwards' lab in Edinburgh of an enzyme that protects the receptor, that metabolizes the cortisol to an inactive steroid. And in the process, that's probably not enough by itself because, that 1,000-fold difference. But it sets the scene intracellularly so that what cortisol does get into the receptor can't act. So it makes an aldosterone selective tissue.
What enzyme?
It's called 11-beta hydroxysteroid dehydrogenase. 11-beta HSD2 is the enzyme. And that, I once read an editorial in Science, the journal Science, entitled All Really Great Lies Are Half True. And, we thought we had the answer then, and we only had half the answer. I'm convinced of that. And the rest of it's now just starting to come out, gradually being accepted, more or less grudgingly in Japan than anywhere else. They're doing really a lot of stuff in aldosterone, particularly clinical stuff at the moment.
Would you sum up what you thought you had, or what the field thought it had in the the end of the 1980s?
End of the 1980s. Well, Ron Evans, who is a friend, a very good friend, had cloned the human mineralocorticoid receptor. And so that was that. He'd shown, at a molecular biological level, that it was expressed in the brain and in the heart and those other non-epithelial places. And we thought in the end of the 1990s that clinically aldosterone wasn't terribly important, that autonomous aldosterone secretion, that's primary aldosteronism, was maybe 1%, if that, of all hypertension and was pretty benign. And we had drugs that would affect the renin-angiotensin-aldosterone system, the ACE inhibitors and the early angiotensin receptor blockers, and they were fine in hypertension, they were fine in heart failure. We didn't need much else. It was a lull before the storm.
How did you feel in that lull about your career as a researcher?
Oh, well, I could keep on doing stuff. That wasn't the issue. I'd spent much of the 90s trying to run a research institute, the Baker Institute in Melbourne, with a lot of administrative and managerial and fundraising and stuff to do, some of which I enjoyed and some of which I didn't. And in fact, in 2001, resigned or retired from that. Being an institute director used to be a life sentence, but increasingly it's not.
How did you get to the Baker?
I applied to be director and was appointed director in 1989. Because it was up the tree. I was 49, and I thought, well, this is the way to finish off a career, to be the director of an institute and of a well-established, started in 1926 research institute in probably the second biggest of the teaching hospitals, and it's the Brigham and Women's rather than the Mass General equivalent in Melbourne, the Alfred Hospital. And I did a small amount of stuff. I had some very good Japanese postdocs and some very good technicians while I was at the Baker, but I was really pretty distracted by having to administer. And I think I've done more proper thinking and, parsing of areas and issues since not having a full-time day job. I mean, being very, very, very busy doing a whole bunch of stuff, but not having those responsibilities. And not having a lab, not having fellows, not having students. Lots of collaborations. Then I was, in the decade I was, notionally at least, master of all I surveyed. I mean, I didn't have any time to do anything. Well, and people had their own programs, and that was terrific in the place. I mean, I couldn't tell this one to do this and this one to do that. I mean, they don't work like that. So,
what was happening to the consensus around it?
Well, the consensus was broken, and it was broken in a number of ways. In the first decade of this millennium, well, a little earlier than that, in the last decade.
So when are you talking now?
I'm talking in the late 1990s, let's say. It was broken in two ways. One was the publication of what's known as the Rales trial, which is the randomized aldactone study. And it was to give spironolactone, a mineralocorticoid receptor antagonist, on top of standard of care to patients who were in New York Class 3 heart failure. These are patients who've got about, even with treatment, about 2 years to live on average. And so a low dose of spironolactone, the average dose was actually 26 milligrams a day. The smallest tablets, 25 milligrams. On top of standard of care, gave an astonishing 30% improvement in survival and 35% fewer hospitalizations. I mean, whoa. 35% fewer hospitalizations. Even the health economists get interested. So that told the cardiologists that something was happening here. Now, they all thought it was aldosterone. I think increasingly evidence is not. It's mineralocorticoid receptor activation, but it's activation by another hormone in damaged tissue. Whatever. The second paradigm shift, to use that perhaps fairly hackneyed phrase, was the demonstration that primary aldosteronism, autonomous aldosterone secretion, was not a minor benign player in elevated blood pressure. I think there's now, around the world, international consensus that it's probably 10% of all hypertension, that it is much more dangerous than the hypertension, essential hypertension, by studies on age, sex, and blood pressure matched controls. If you've got primary aldosteronism, you've got four times more likely to have a heart attack, up to 12 times more likely to have atrial fibrillation, which flicks off things and you have strokes. It's not a good disease to have, and that made people think. So in the last decade and a bit, aldosterone's really come sort of back into prominence. Now, it's been enthusiastically adopted by the cardiologists who, before that, never even thought about it. There are 10 times more cardiologists than endocrinologists in most countries. They tend to be terrific in many ways. I mean, if I need a stent, I'm going to go and see a cardiologist. But they're the sort of orthopaedic surgeons of medicine, you know, fix it and forget it, boom, boom, boom. And they work on the principle of a little bit is good, a lot will be better, many of them. And it's not been necessarily totally plain sailing since then, given that this, you know, large group of sort of half accepted that it's probably good to use a mineralocorticoid receptor antagonist in heart failure.
So the Rales trial, how did the how did it cause the consensus to be realigned, or was it just a temporary?
No, it's not been temporary at all. I mean, it's been followed by 2 other trials, one called Ephesus, which is using, well, what Rales did was to say, hey, we need a new mineralocorticoid receptor antagonist. I mean, spironolactone was patented more than 50 years ago. And it's a very effective drug with nasty side effects. It's, in addition to being a mineralocorticoid receptor antagonist, it's an androgen receptor antagonist. So if you antagonize androgens, you get erectile dysfunction, can get, and gynecomastia, which is enlargement of the male breast. It's also a progesterone mimic, so that in women who are cycling, it throws their cycles out and so on. So it's a dirty drug. So that sparked the industry, in particular G.D. Searle, which was then taken over, etc., to develop a second-generation antagonist, which is called eplerenone. They did, and then there have been trials with eplerenone Ephesus. You'd never put eplerenone head-to-head with spironolactone. Spironolactone is better, except it's got these dreadful side effects. So they did it in heart failure post-myocardial infarction. And it was good, it worked. It improved survival and fewer hospitalizations. And then more recently, it's been done in New York Class 2 heart failure, a trial called Emphasis. And again, it's been shown to be very useful. So no, it's been, constantly shown in the province of the cardiologists, which is heart failure. It's not that they've set out to deny anybody else. The point is that outcomes are easy, relatively. People die or don't die, and you can compare curves diverging in terms of mortality, body bags. The big use for these drugs clearly is not in heart failure, but in high blood pressure. People in their 40s and 50s and 60s with high blood pressure. I've turned into rather a crusader for putting in low-dose spironolactone or eplerenone into, first-up treatment. Somebody comes in with high blood pressure, make sure it's not white coat hypertension or, that they're nervous and so on. Okay, they've got hypertension. I'll put them on an ACE inhibitor and very low-dose spironolactone. Very protective of blood vessels. 999 people with primary aldosteronism never get screened, let alone diagnosed, let alone treated, and it's magic for them, and so on. So I've turned into a crusader for that.
Could you say a little bit more about the Rales trial and the effect and the initial hypothesis that was based on it and how that...
Okay. The initial hypothesis was that it was based on animal studies, that if you gave aldosterone in excess to animals and you needed to give them a bit more salt as well, they got high blood pressure and their hearts got bigger and ultimately they went into heart failure. And on the basis of that trial, Rales was set up in patients with heart failure, progressive, severe heart failure. Half of them dead at under 2 years or under 3 years. And the results of the Rales trial were fantastic. 30% improvement in mortality, survival, 30% better survival, and 35% fewer hospitalizations. That's wonderful. There are 2 enigmas. The first is that the dose of spironolactone added to conventional therapy that caused this wonderful result was very low. The average dose was 26 milligrams a day, and the smallest tablet's 25 milligrams. And the second thing is the aldosterone levels were low normal. I mean, if it's blocking aldosterone, what's happening here? And there's nothing abnormal about the sodium. That was all fine. And that proved important in the next almost 10 years, dissecting just what's happening here. Now, the second of those, which is, how can this happen when aldosterone levels is low normal, I think it's now accepted that in the context of tissue damage, and of course that's part of heart failure, the cardiomyocytes, the muscles under a lot of stress, those mineralocorticoid receptors in the heart muscle cells will be filled with cortisol, and somehow, we don't know the mechanism, we can make suggestions, somehow under those conditions cortisol mimics aldosterone. You get the same sort of effect as you got experimentally with rats and so on when you gave them lots of aldosterone. I think that's pretty well accepted now. What's been longer coming is an answer to the question of why was such a low dose of aldosterone effective? Why was such a low dose of spironolactone effective? The answer to that question, why was such a low dose of spironolactone effective, seems to have come from studies, again on rats, on an isolated rat heart preparation. It's called a Langendorf beating rat heart. It looks awful, hanging down, blood going through it. So. And if you tie off one of the big coronary arteries, the rat has a heart attack. You tie it off for half an hour and then let it reperfuse with the the saline buffered solution, and you get an area of a myocardial infarct of dead tissue, and where the cells are undergoing apoptosis, they're dying. And other people had shown that if you put aldosterone into the perfusing fluid, the infarct got bigger, and the apoptosis got more pronounced. Okay, and you could block that with spironolactone. We showed that if you put cortisol in at very low doses, exactly the same thing happened. The infarct got bigger, so that supports the interpretation that, hey, in the Rales trial, it's cortisol, not aldosterone. And you could block that with spironolactone. And then just to be sort of ultra careful, we took hearts and just put in spironolactone. And what happened then was the infarcts got smaller and the apoptosis got less. So the spironolactone was having an effect on its own, of its own accord. So when we thought, well, maybe there's some, aldosterone or glucocorticoids hanging around. So we adrenalectomized animals, took out their adrenal glands, the source of all this. A week later, did it again. Spironolactone is protective by doing things in its own right. And at the meeting here in Boston, the beginnings of unravelling that are going to be presented. And were presented yesterday at the aldosterone meeting. And it's wonderful because what spironolactone does is to induce the synthesis of protective proteins and repress the synthesis of pro-apoptotic proteins. The pharmacologists call that an inverse agonist. It's actually doing stuff. It's not just sitting there like the key to the trunk of the car in the ignition. It's doing stuff of its own accord. And it does it at very low concentrations, experimentally. And if we extrapolate that to the clinic, we can say, well, that's maybe why you only needed 26 milligrams of spironolactone to get that effect, because it doesn't have to block out every last molecule, just has to get a few of its own in, and then, hey, suddenly it's changing the balance. So that's been wonderful. Now, that's yet really it's only 18 months old. I mean, it's a bit like turning around the Queen Mary. And there needs to be a lot more studies. I mean, that's an initial study, but it's unequivocal, what it tells us, which is spironolactone isn't just a blocker. It's doing stuff of its own accord, which is very protective. So Rales has been I mean, I think probably a good word is prismatic. It's actually sort of opened up white light into a series of different spectra and allowed us to ask different questions. It's been good.
Why did you leave the Baker Institute?
Oh, I left the Baker Institute because...
This is in 2001.
2001, end of 2001. Well, a number of reasons. I think, my wife died in the middle of 1998, and that was really hard time, very hard time. I'd been there since 1990, and I think it was probably just time to go. I'm not a very good manager. I hate taking file notes when people come and see me in case something happens and lawyers get involved. All that. I mean, that really drove me mad. I was 61 at the end of that year, and I thought, well, I'll do some other stuff. So I did. I decided in about 24 hours. I thought, back it. I'll get a life. It's no great fun, often, for some people, and I think it was for me, and I know other people who've been in the same situation, to, spend probably 40 or 50 hours a week administering, when what you really want to be doing is thinking and testing and wondering and writing. I quite like writing and sending stuff off and talking about it and so on. And I've done that much more since I've been not having had a day job. I've actually been busier in many senses, but I can choose what I want to do. It's wonderful.
So you're based at Prince Henry's? You left the Baker for Prince Henry's?
Well, I'd been at Prince Henry's until I went to the Baker. Prince Henry's moved, and then, as soon as I left the Baker, various ones said, will you come to Prince Henry's? Will you, come to Melbourne University and so on? So,
but that's not a day, you don't consider that a day job?
Well, no, it is a day job, but it's not a sort of, 8 till 6, 5 days a week day job. It's not a consuming day job. I can choose now what to do, who to collaborate with, where to go. I've still had a number of jobs since then, but none of them have been full-time. I was Director of Research Strategy at the hospital for 2.5 years, which was not terribly successful because the powers that be in the hospital are research naive and ignorant. I mean, that's not true of all the hospitals in Melbourne, but this one, never mind the quality, just feel the weight. Hopeless, absolutely hopeless. Talk about turning around the Queen Mary. This is like turning around the Titanic. So I finished that at the end of 2010. I've now got, notionally 1 day a week, and well paid for 1 day a week, a job as Executive Director of Obesity Australia, on the basis I think that it takes one to know one. But and that's actually terrific. It's a very interesting area. This tsunami of obesity that's hit America, Australia, and so on in the last 25 years. Multifactorial. Everybody thinks it's the fault of the obese person. In many instances, that's not necessarily the case because there's now wonderful evidence for preconception, intrauterine and early life programming of set points for hunger and satiety and particular tastes, for foods in the early post-weaning life. But there's a lot of high energy dense foods and, people are doing sedentary jobs rather than working in steel mills, etc., etc., etc. So it's very complex. It needs to be addressed both, globally here in America, in developing countries, in China, in Shanghai, there are a lot of very obese people, almost half of whom will develop diabetes, perhaps more in Shanghai than in America or Australia. It's probably closer to 40%. But even apart from the diabetes, the lost productivity, the medical costs are going to be crippling. We've got to do something about it. And the administrators, at least in my country, know about this and are worried stiff about this. The politicians are very short term. It's the next electoral cycle. And so Obesity Australia is, a lot of people are not necessarily invested in it. You know, they're not diabetic carers or they're not scientists working there. A lot of sort of high profile people who have come together and have been animated by this, and it's a wonderful thing to do when you're getting old and grey. And it's a source of constant wonder. How are we going to juggle all this? How are we going to do it?
I wanted to ask you a little bit about, you mentioned politics, research, representation.
Oh, okay.
I'd like you to get a chance to talk about that.
Well, I don't know where it began, really. I was a keen debater at school. I won the Victorian impromptu speech in my last year at high school, which is no great accomplishment. But I was a university debater, you know, college, university, InterVarsity, in fact some international debates too. So that was one thing. But in residential college I was in at Melbourne, I was on what was called the General Committee, you know, the student body, and then was elected president of the student body. And I was on the Student Representative Council as a freshman at the university. I mean, God, what is this? And I liked doing stuff, writing stuff for the student newspaper and so on. And that continued when I was a PhD student. I used to write opinion pieces for one of the local sort of semi-intellectual journals, monthlies, and I was also the wine correspondent slightly after that for a fairly scabrous, a bit like the Berkeley Barb, scabrous weekly. And I guess I got really into medical research politics. We had a crisis in funding in 1976. I mean, the figures are now ludicrous. There'd been a glitch in the budget allocations or something, and we were suddenly faced with $850,000 to fund 6 months of the medical research being done in Australia. I mean, it wasn't very well funded, and, you know, that's 35 years ago, but hang about, that's not very much money. So 4 of us, John Coghlan, who'd been my mentor at the Florey, John Chalmers, who's a wonderful, charismatic, spiky cardiovascular physician, Tony Baston, who's an immunologist. The 4 of us became known as the Melbourne Mafia, even though John Chalmers was in Adelaide and Tony Baston was in Sydney. And we used to go up to Canberra and talk to politicians. I mean, it was back then, you know, there weren't all the spin doctors and the minders and the barriers and God knows what. And so we got that turned round, and from that stemmed a continuing interest in medical politics. I was president of the Australian Society of Medical Research in 1979, which was the Young Turks. You had to be under 40 to hold office. And you had to write a one-pager to go in the annual meeting thing about, you know, what you thought about stuff. And I wrote this thing called All Really Great Lies Are Half True, which is being asked for evidence-based outcomes of what your research would do. I mean, you didn't know till you got the results of the research. It was sort of crazy. And I was so pleased with this, I thought, I'll send that off to Science. So I did. And for the first time in my life, I got back the galley proofs as acknowledgement. It was wonderful. And it's called All Really Great Lies Are Half True. And I still, I wouldn't change a word of it now, I think. And then, I don't know, I just got, I was on the council of the Australian Endocrine Society and then was president and became more and more involved in the affairs of the Endocrine Society, our Endocrine Society, the one in Washington, and was on journal editorial boards, but then particularly on the working groups and then the committee to deal with international things, and was immensely honoured to be the first non-North American to be elected to the Council of the Society in 2002. And I regard this society as my intellectual home. It's got fantastic collegiality is the word. I mean, Scott Hunt, who I think is terrific, uses the word of approbation he uses of the society is nimble, and that's true. I think it is in many ways. Occasionally lumbers, but it's usually nimble. But it's somewhere where, from the practitioners to the physician scientists to the basic scientists working in the lab, even though there have been tensions in the past, it's a totally collegial, wonderful group of people. These are my peers, these are my friends. Walking around this morning in the hall in Boston, I've seen and greeted 100 people. And most of the people under 50 I don't know, for heaven's sake. These are the old stagers. It's an extraordinary organisation. I've never been in an organisation, except perhaps those early days in the Australian Society for Medical Research, when we were going up to Canberra and knocking on doors and taking the treasurer of Australia to dinner, just him and me. And he said, "Why are we here, John?" I said, "I need your help. I need you to tell me who I should contact to make sure we don't have another fiasco in the budget." "Oh," he said, "that's easy. Start writing down the names." Of course, I've got him. And in the archives of the Australian Society of Medical Research, this is after this 1976 nonsense, a couple of years before, there's a telegram. I mean, this is before, telegrams were still in. "Dear John, medical research budget has gone from $14 million to $18 million. Now are you happy? Philip." It was Philip Lynch, the Commonwealth Treasurer. And I telegrammed back, "Philip, happy, yes. Satisfied, never. John." That's been lost, that one. But so it's been a long involvement in medical politics. And in fact, this Obesity Australia thing I was speaking about, that's essentially political. I mean, we need to change community attitudes. We need to change, which will allow politicians to do stuff which they need to do, and we have to change community attitudes on the basis of the best evidence there is, the best wisdom there is. So it's really a political organisation that I'm chairing, and in fact executive chairing. I wish there were a CEO. But we can't afford one yet. But we'll get one.
Now, what about the guidelines for the primary elder?
Okay. Well, this has been interesting because
could you set this up, like how your role in getting even the guidelines?
Yeah, it was terrific because I'm an aldosterone physiologist. I'm a rat doctor, really. I do stuff with rats and mice and sheep historically and so on. It's been a long time since I've seen patients, but the vagaries of treatment, of the way people handled patients with primary aldosteronism, it seemed to me ripe that we needed to try and get a little bit of consensus into this, not to shoehorn people into, So I was at a council meeting in Sonoma, of all places. Each winter, just in January, there's a meeting of council and committee chairs, so I proposed this, I think, to the then chair of the Clinical Guidelines Committee, and Bob Utica. And he said, "Well, we've got a full dance card for next year 4, but I'll see what the committee thinks." And the committee says, "No, we ought to do that. The time is ripe." So.
And which committee is this?
There's an overarching committee within the Endocrine Society called, I think, the Clinical Guidelines Committee. And what I was then chair of was the particular task force to develop clinical guidelines for primary, case detection, diagnosis and management of primary aldosteronism. Money was tight, it's always tight, so we could only have, I think, 6 people on that task force. And I wanted it to be international. 2 of the outstanding people are Bill Young at the Mayo Clinic, who's the incoming president of the society, which is terrific, and Michael Stowasser from Brisbane. So there were 2 Australians on it. I mean, this is, mad.
Who else was on the committee?
Carlos Fadela from Chile, Franco Montero from Italy, from Padua, Celso Gomez Sanchez from Mississippi, and that was our complement, except I managed to persuade the powers that be that we should add Bob Carey. Bob Carey was then the president of the Council of High Blood Pressure Research, deep in the toils, the political machinations of American Heart Association, and was incoming as president of the Endocrine Society. So he was the bridge man. And so we worked for a couple of years, teleconferences, emails back and forth, a couple of face-to-face meetings, developing, thrashing out a consensus. I mean, it's not what all those people do necessarily. I mean, they do variations, but a set of, in a sense, guidelines. And, I'm the person with far the least experience, hands-on experience in that process. I learned a lot from those people. And I've now been able to stand back a bit and say, but we're missing the wood for the trees. If 10% of the people with high blood pressure have got primary aldosteronism, if you take America, 20% of the people in America have got high blood pressure, so 2% of the American population, we're talking 6.5 million people. In Dallas-Fort Worth, which drains 6.5 million patients, they've done 250 operations for primary aldosteronism in the last 10 years. We are missing the wood for the trees. And so, I have no personal investment, in a sense, in it, but I've become a crusader for looking at hypertension differently because we're missing all the people with primary aldosteronism. The guidelines, I think, have been useful. They're work in progress. They have to be. They're not set in concrete. Already there have been things that I've edited a journal volume, quarterly reviews in endocrinology and metabolic disease with a whole lot of people who weren't on that committee. There's nobody from Japan, which is now really the epicenter of studies here. So I had 2 Japanese and Germans and so on. And, it's work in progress.
What about your current views of the field?
Well, there are always new things to do. I was privileged to review a very good paper in Science, which was published in Science in January. And I was then asked to write an editorial commentary about it, showing that about 35-40% of primary aldosteronism, these little benign tumours, adenomas, they don't metastasize, they don't spread, they can cause a lot of trouble, due to a mutation in a particular potassium channel, KCNJ5. And so I wrote the commentary and, pointed out that there were things that would flow from this and so on and so on. At the current meeting of the Endocrine Society and at the meeting of the aldosterone conference, just precedes the Endocrine Society, there are papers describing a total, I think, of about 800 of these tumours, showing the same sorts of proportions. And 2 papers have been submitted to a journal, from 2 different groups, studies from all over the world, clunk. I mean, this is heady stuff. The most recent paper I've published in collaboration with a spectacular postdoc called Karen Kassan from Brisbane, where I have an honorary appointment, is, I think, probably the definitive work on the evolution of the mineralocorticoid receptor. I mean, nothing's definitive in evolution really because we weren't there, but there's been a back and forth about which is the eldest of the family members of the four closely related mineralocorticoid receptor, glucocorticoid receptor, androgen receptor, progesterone receptor. And the argument's gone back and forth, but I think we've nailed it. Clunk, which is good fun. I think aldosterone's here to stay. I think the mineralocorticoid receptor has still got a lot of things that we need to find out about it. We're really not terribly across what it does in the brain. We don't know if it has a physiology as opposed to a pathophysiology, for instance, in the heart. We don't know if it's what it's doing, in your healthy heart or hopefully my healthy heart. We do know what's happening to that, what that receptor's doing, and how we can ameliorate what it does in heart failure and high blood pressure. So there's a lot of stuff to do there. Aldosterone itself, probably less, because the drivers to aldosterone secretion, the main ones, tend to be, changes in sodium and potassium, which is what it affects in the kidney, and changes in intravascular volume. If you lose a lot of blood, you really need to hang on to water and sodium to bring back your blood volume. That physiology's, well ensconced, well accepted. Everybody knows that. There's no question about that. So I think aldosterone's here to stay. The future is with the mineralocorticoid receptor and what else it sees and what else it listens to and where that happens and what that means. And if there's no physiology, what's the pathophysiology? I mean, why have we got it to make things worse in heart failure? Why is the receptor in the heart muscle if it doesn't have a normal role? Well, it probably does have a normal role. I mean, evolution is, you tend to get rid of things that you don't really need. Now, I'm not sure why we need sinuses or a vermiform appendix, but the C-peptide that joins the two active bits of an insulin molecule has got 10 times more mutations in it than the insulin itself, because it's important that insulin stays as insulin. It doesn't matter what happens to the belt that, as it's read off, holds them together. Stuff like that. So the receptor's still, I think the receptor will see me out.
Thank you.
Yeah.